Hi, my name is Anirudh and I'm the founder of iRasus. iRasus is an electricity data analytics company specializing in industrial IoT and digital transformation of the energy storage sector across electric mobility and stationary energy storage applications. We equip manufacturers and bulk users of batteries and ancillary power equipment with the software products for various business processes, ranging from new product development through operations and maintenance and all the way to end of life. We address pressing issues in the safety, reliability, durability, and affordability of energy storage infrastructure that is catalyzing the energy transition and decarbonization of the power and transportation industries. Across all use cases of our offerings for a target customer base of OEMs, electric vehicle fleet operators, as well as commercial and industrial behind the meter service providers globally, is a $3 billion market in the present decade, and we estimate the potential to mitigate over 10,000 metric tons of carbon dioxide equivalent emissions per annum. Essentially, we identify assets or the assets that are exhibiting anomalous behavior on the basis of a large number of custom fields, each of which are configurable in nature. And the idea is to look at the past, present, and the future. And in terms of past, we look at root cause analyses of failures, any faults that might have happened on field or when the batteries are present inside of the charging stations, the swapping stations. The present behavior is used for operations, anything which is related to swapping, billing, for example, and several other business models. And finally, we look at the future behaviors of the batteries that are based on exceedance probabilities of failures or faults that might occur 120 days in advance. Just to look at an individual asset, so I'll take an example of a battery that is discharging. And what we see on the screen is what we call the level A pack data. This is something which any battery, whether it's present for mobility applications, stationary storage such as the ones in telecom towers, solar inverters, or finally consumer electronic devices would be sending to us. And some of these measurements, namely voltage, current, state of charge, temperature, remaining charge capacity, and so on. And towards the right of the screen is a set of two matrices that are very specific to the mobility fleet operator TG. And the idea is to understand how many kilometers have been traveled since the last charge, as well as how many kilowatt hours has been discharged. The use case of this is in trying to understand distance to empty, as well as how many kilowatt hours are left between now and the duration through which the battery might discharge to empty. Further down, subsequently, the characteristics are more useful for battery pack manufacturers in comparison to battery fleet operators. And the idea over here is to understand the current drawn by the motor controller while the battery is loaded inside of a vehicle, or alternatively, when the battery is charging inside of the stations, inside of the pods. What is the CCCV profile that the battery is currently drawing current from the chargers? That gives an idea of the C rates and ultimately at an aggregate level, indicators of degradation, state of health, and so on. The next graph that we see is also useful for battery pack manufacturers, and this illustrates cell voltage imbalance as a function of the individual voltages of the cells. What we've gathered in the past, having analyzed so many batteries over a long period of time, is that there's a significant correlation between repeated incidents of high cell voltage imbalance with premature degradation. And some of these aggregates are what the numbers that we crunch and subsequently feed into certain business intelligence tools. In order for manufacturers and fleet operators alike to consume in some of their business processes at any part of the battery's life cycle. Also of interest over here is the temperatures of the individual cells that we measure along with the voltages. That also plays a significant role in understanding incidents of overheating that might trigger, in addition to degradation, certain adverse effects such as spontaneous combustion or a thermal runaway, for example. The next part is that we have an integration with a plain vanilla vehicle tracking system, which most fleet operators have been using with their internal combustion engines for quite a few years now. The idea over here is to enable the transition from ICE to electric mobility, either leapfrogging lead acid batteries or going through the lead acid battery route entirely. And some of the opportunities which fleet operators have in the context of their raw material management that they use a vehicle tracking system for is in understanding matrices such as the current being drawn by the motor controller, distance to empty, and how does the battery deliver the power necessary for the vehicle to travel for a certain distance or complete a certain trip. And some of the matrices which decide that are in terms of correlating the battery data with the location data. So we see that for every unit percentage drop in state of charge, how many additional kilometers have been traveled, and so on. So some of these at an aggregate level for an individual battery over a longer period of time, or for an entire fleet of batteries over a longer space or a larger space, or both of these put together, larger space and time, would make much more sense for manufacturers and fleet operators alike. And the final part is what we call level B data. This is something which is based on individual measurements that we collect from the sensors inside of the battery management system. Some of these are tied to use cases which are SLAs between the manufacturers as well as the buyers. One of the examples of this is in the cycle level data. So, any manufacturer of any battery pack would be quoting that a certain product would be capable of operating in the field for a figure of somewhere between 700 and 800 cycles. And there are certain other products which might last for upwards of 1500 cycles. So the idea behind this part of the interface is to look at individual cycles according to the definitions of the manufacturer, and also correlate that with the geographical data we've collected in terms of mileage, in terms of the odometer measurements, and so on. One of the most interesting matrices over here is to look at the kilometers per percentage state of charge, in addition to the current or speed, in addition to percentage state of charge. This mileage metric, when used aggregate across an entire fleet for a day, determines a lot of the key operating matrices. And that's what drives revenue and the measurement of utilization of the network for the fleet operator. And in addition to this particular dashboard, we have individual dashboards for certain other business cases. So, for example, batteries that need to be refurbished. So, we see a lot of those incidents. Batteries that are being stolen, we see a lot of that as well. And certain fleet level dashboards and dashboards which help in identifying degradation for an individual battery over a longer duration of time. And all of these feed into business intelligence models via data acquisition mechanisms that are separate from the dashboard. That said, in addition to the dashboard, we have real time APIs which work on either a push or a pull based mechanism. And we do send a lot of data onto other software products which our clients use, whether those are for business intelligence or for any other kind of analytics which might be specific to their business case. We also have integrations with ERP systems and a lot of other similar software products. We currently manage a fleet of over 3,000 batteries across the use cases present for electric rickshaws, larger capacity battery packs like electric buses.